Hi, this video is for Unit 6, Lesson 3. We'll be graphing rational functions. I want to start by looking at each of these three expressions and deciding what they are equivalent to. First expression is 0 divided by 8. If you take 0 and you divide it by 8, you get 0. And it really doesn't matter what you divide by as long as it's not 0. 0 divided by any number is equal to 0. 8 divided by 0 is our next expression. If you remember from prior years, or if you try typing this into your calculator, you might find that you get an error. We usually say that that is undefined, or sometimes no solution. Last one has lots of zeros in it. We'll be having some expressions that look like this come up today in the lesson. So I wanted to review how to simplify this. In the numerator, we have 0 squared, and we're adding 7 times 0, and we're subtracting 12. That's equal to negative 12. In the denominator, we have a 0, and we're subtracting 4. That's negative 4. So this expression is equal to negative 12 divided by negative 4, which is 3. All right, so we're going to be graphing rational functions today, and unlike other function families that you have graphed in the past, a lot of different shapes can come up. The one that's shown right here is probably the most basic rational function, and it has two parts. It has this part here, and I'm not drawing it perfectly, but you get the idea. And it has another part up here, and those two parts are not connected, and they're usually called branches. We'll be looking at some rational functions that look like this one or similar to this one. We'll be looking at some that are quite a bit different. Now, rational functions have what are called asymptotes, and they are lines that the function gets very, very, very close to. Sometimes they have vertical asymptotes, and the ones that we'll be graphing this year always have a horizontal asymptote. In other years, you might look at other sorts of asymptotes, but this year we'll be limited to vertical and horizontal asymptotes. Asymptotes are lines that the graph gets infinitely close to, and so you'll get used to graphing those. They are not actually a part of the graph. We often graph them with rational functions just to help us as we're sketching to get the function placed correctly. Here's a couple more to look at. That first one we looked at is shown again right here at the beginning. The one in the middle actually has 3 branches. It has a branch over here and a branch up here that are a lot similar to that first graph I showed you, but then it also has this graph in the middle. When a rational function has a vertical asymptote, it will never cross that vertical asymptote. Vertical asymptotes are maybe like fences that they just cannot cross. Horizontal asymptotes, the function will sometimes cross, like you can see right here, it crosses that horizontal asymptote. And that's because the horizontal asymptote is kind of like an end behavior asymptote. Instead, when we studied polynomials last unit, the polynomial's end behavior was often to grow very, very, very large, or to approach positive infinity or negative infinity if it was getting farther and farther in the negative direction. Rational functions, or at least the ones that we'll be graphing this year, their two ends on the far right and the far left approach the same number, and that number is the horizontal asymptote. This last one shows you an example of one that has an asymptote that is not horizontal. This year we won't be graphing any like that, but I wanted you to understand that they do exist. And asymptotes can be other shapes as well. Asymptotes could be a parabola or some other shape. I do think it's helpful when you're graphing rational functions if you graph the asymptotes in different colors, like in red, so that you remember that they aren't the function themselves. They are just some sort of imaginary lines that govern the shape of the function. So we're going to look through 4 graphs together that we're really going to be focusing on connecting the equation to the placement of asymptotes and intercepts, and then we'll do a few that we do from start to finish. As we're graphing these functions, you can use Desmos.com, either the website or the app, or if you have a graphing calculator, you can use that. With the graphing calculator, in a minute when you start graphing them, you will need to be mindful of using a lot of parentheses around the numerator and the denominator, otherwise you can get errors. So if you're having problems getting the shapes that you need, talk to your teacher about how you're inputting the function, because that can make a big difference. Okay, so here's our function. We're graphing the function x plus 1 divided by x squared plus x minus 6, and it has its factored form shown there as well. We'll be looking at factored forms of functions quite a bit. So if you type this into your calculator, it shows you that the shape of the graph is something like this. Now, I already placed the asymptotes onto the coordinate plane, and we'll practice that later, but for these first couple, I just placed them for you. So you can see the shape. It has a branch sort of down here nestled between these 2 asymptotes. It has one that sort of comes down right next to that asymptote and then curves over through that intercept that I had marked, and then continues down. And it has its 3rd branch up here. And this year we'll be using technology. We'll be using either the graphing calculator or Desmos to graph all of these equations and to get their shapes. Now that we have that sort of sketched, I want to think about the equation and the graph and see if we can draw a connection between the two. In the numerator, we have a factor of x plus 1. So what is happening on the graph at the x value -1? We've worked with polynomials a lot, relating the roots to the factors, and if I see a factor of x plus 1, it immediately makes me think of that x value -1, and on the graph you see that -1, at the x value -1, we have an x-intercept. We've got 2 more factors in this function. We have factors of x plus 3 in the denominator and x minus 2. So I'm wondering what's happening at the graph at the x values -3 and +2. And if we come over and look at our graph, you can see that at -3 and at +2, those are the locations of our vertical asymptotes. So in the numerator, our factor is giving us the location of the x-intercept. In the denominator, our factors are giving us the location of the vertical asymptotes. Let's look at another function. Oh, there's my Lord of the Rings joke of the day. It's a good one. Whoops. Okay, so some rational functions have things that are sometimes called holes. They're called holes because we draw them with these sort of empty circles. They're also called discontinuities. They're infinitely small breaks in the graph, so we kind of just show them as an open circle. So here's our function, 4x to the 3rd power minus 12x squared is being divided by x to the 3rd minus 3x squared plus x minus 3. So if we factor this function, it looks like this. And if you graph the function in your calculator, it looks like this. Now, I'm going to go ahead and sketch that on my coordinate plane. It looks like right here it comes down right to the origin. It's going along this asymptote, kind of dips down, and then comes back up. like so. Okay, well, maybe I'll leave that for a second. So this function does have a discontinuity, and I drew it on the graph coordinate plane before we even started sketching because I wanted you to see it there. But I want you also to notice that you cannot see that discontinuity on the calculator screen. It doesn't show up there. And the reason it doesn't show up is because it is infinitely small. If you looked at the table, which I should have pulled up, but I didn't, if you looked at the table, you would see an error on the table for the x value of 3. So if we look at the factored form, we have been practicing simplifying rational expressions for a couple of days now in class. So you might notice that in the factored form, we have a factor of x minus 3 that reduces. So this is exactly equivalent to the equation 4x squared over x squared plus 1. So when you have a factor like x minus 3 that reduces, what that causes on the graph is it causes at that x value of 3, it causes a little discontinuity in the graph. So you can get the location of the hole from any canceled factors. And it's important to try to remember to draw those on your graph. Essentially what's happening is at the x value 3, if you substitute it into the original function, for x, like so, what you end up with is the expression 0 divided by 0, which is undefined, like we talked about at the very beginning. So for the x value 3, this function is undefined. But it's only the value 3 that gives it problems. If you substituted, for example, 3.01, you would get a number, between 3 and 4. If you substituted 2.99, it would be fine. So it's like just infinitely close to that little hole is just fine. The only value that's giving us problems is the value x equals 3. So some, but not all rational functions will have vertical asymptotes and holes. Holes definitely don't come up on every rational function. And on graph number 2 that we just did, we didn't have a vertical asymptote. So you may or may not have a vertical asymptote and a hole on your function, but they definitely come up on a lot of them. And we find vertical asymptotes and holes by looking at the denominator, and that is because you can't divide by 0. So any x value that causes one of those factors in the denominator to be equal to 0, it's going to cause on the graph the vertical asymptotes and holes. So just scrolling back to those other two graphs really quickly, if x is equal to negative 3, this factor is equal to 0, which causes that denominator to be 0, so that causes one vertical asymptote. If x equals 2, that causes this second factor to be equal to 0. And then on graph number 2, even though it cancels out eventually, it's still a part of that function, so it's causing division by 0 if x equals 3. So anytime you have a factor in the denominator, you want to think about what x value would cause us to divide by 0, because those are going to cause either a vertical asymptote or a hole on your graph. Okay, there's the dividing by 0 joke. See, it causes holes or vertical asymptotes. Okay, well, we kind of already talked about the numerator with graph number 1, but let's look at the factored form of this function, and here is its graph. So we talked about with graph number 1 that the denominator gives us the location of the vertical asymptotes, unless they cancel out, in which case it would be a hole, but this one definitely does not have a cancellation. So this graph is going to have a vertical asymptote at +2 and at -1. And if you look at that graph screen, that calculator screen, you can kind of see those two asymptotes on the graph. The numerator, we talked about that when x is equal to -3 and when x is equal to 4 in this particular case, those are the x-intercepts. So this is going to cross at the x value 3 and at the x value 4, and you can definitely see evidence of that on the graph screen right there. Something that we haven't talked about yet is how to find that horizontal asymptote. We will talk about that in a minute, but I'm just going to tell you that this one is located at the value 1. So if we're sketching this, it has a branch right here that goes through that x-intercept at -3 and sort of nestles between those two. And we have a branch over here that goes through that x-intercept of 4 and kind of nestles between those two asymptotes. The last one, you can see on this graph screen that it has a y-intercept of 6. And I want to talk about in the function how to find that. In the function, the y-intercept always happens when x is equal to 0. So we're going to plug 0 into the function. So we would get 0 squared minus 0 minus 12 divided by 0 squared minus 0 minus 2. Well, that numerator is equal to -12. The denominator is equal to -2. And when we divide -12 by -2, we get 6. So when we plug in 0, we get 6. And that's the y-intercept right there. For any function, you can find the y-intercept by substituting in the x value 0. Now you can kind of see from the graph that it does dip just below that y-intercept. So I'm going to just draw that in as best I can, like that. And we don't need a perfect sketch. We just need, you need to put some thought into it. But it does not have to have exactly the perfect curvature for what we're doing this year. All right, so that's graph number 3. So far we've talked about holes, which they are the result of factors that cancel out. Pro tip, usually I figure out what their x values are first, but then you usually graph them last. We'll do that in a minute. Vertical asymptotes come from factors left in the denominator that did not cancel out. X-intercepts come from the numerator, and then the y-intercept we find by substituting the value 0 in for x. So there's one more feature that we need to talk about, and that is the horizontal asymptotes. These are usually the most tricky for people to find, or at least at first. I usually call them end behavior asymptotes because I want you to focus on the fact that these asymptotes are telling us what is happening on the far left and the far right side of the function. All rational functions have an end behavior asymptote, and they depend on the degree in the numerator and the degree in the denominator. So for this first function, f of x equals 1 over x plus 3, the highest degree is 1, and it's found in the denominator. And so the end behavior is going to be at y equals 0. Now that's because as x gets larger and larger and larger, we end up with 1 divided by a big number. And 1 divided by a big number just gets closer and closer to 0, the larger that number gets. On the other side, so that would be the right-hand side, on the other side, if x gets closer, or if x is getting more and more negative, we get 1 divided by a really big negative number. And again, if you have 1 and you're dividing by a big negative number, it's just going to get closer and closer and closer to 0. So the far left and the far right side are getting closer and closer to y equals 0. And it's going to be just like that for any function in which the highest degree is in the denominator. So for this function, our numerator is degree 1, our denominator is degree 2. The highest degree is found in the denominator. It's going to have an end behavior at y equals 0. And you can see that on the graph there. And one more of these. Highest degree of this function is found in the denominator. So it's going to have an end behavior asymptote at y equals 0. Now once again, keep in mind the function can go across that. You can see it going across the end behavior asymptote right here. The end behavior asymptote is just telling me that on the far left and the far right of the function, the y value is getting closer and closer to 0. So that's one of the potential scenarios, is that we have that highest degree in the denominator. Another possible scenario is that they have the same degree in the numerator and denominator. If the rational function has the same degree in the numerator and the denominator, we look at the ratio of the leading coefficients. So in this case, our function has the same degree, degree 2. And if we look at the coefficients, it's a 3x squared over a 1x squared. That's a ratio of 3 to 1. So the y is going to approach the value 3 on both the far left and the far right. Here's another one. Same degree in the numerator and the denominator. In this case, they're both degree 1. So we look at the ratio of the coefficients. The ratio of the coefficients, we have an 8x divided by a 2x. That's going to get closer and closer and closer to the value 4. So you can see that end behavior asymptote is at the value 4. The scale on that graph is counting by 5. So I hope it's easy enough for you to see that it's at 4. One more of these. Here's a function. That numerator is not in standard form, but it is a degree 2 numerator with a leading coefficient of -9. Denominator has the same degree, degree 2. So if we look at a ratio of those leading coefficients, it's a -9 over a 2, which reduces to a -4.5. So you can see on the graph that it has that horizontal asymptote governing those two ends, the right and the left-hand side, get closer and closer to -4.5. So it can be a little bit tricky to find these end behavior asymptotes at first, but you will definitely get the hang of it. We will not study this year the ones that are not horizontal. Those occur when the highest degree is found in the numerator. So in this case, you would get either a slant asymptote or maybe a quadratic asymptote. They do exist. If you take pre-calculus, you'll work with those more, but for this year, we will not be worrying about those sorts. Okay, so we're going to go through some graphs from start to finish, and it's a lot of graphs to go through. We're going to go through 5 graphs, but I want to do this because some different scenarios come up, and it's really tricky to get used to this. So first thing I usually do when I'm graphing a rational function is graph it in my calculator or on Desmos to just see what the shape is. So if you put this function into your graphing calculator or Desmos, and again, if you're using the graphing calculator in particular, you want to do some parentheses there. It looks like this. We've got a couple of branches. I'm just going to kind of sketch that general shape right here. I'm going to tuck it away now. So I usually look at the shape first because that helps me know as I'm finding my asymptotes and intercepts if I'm on the right track. So the second thing I usually do is factor it. So the factored form of this function is x minus 7 times x plus 2. And the denominator is going to be an x minus 4 and an x plus 2. So right away when you factor it, you might notice that the x plus 2 is going to cancel out. That's going to give us a whole at the x value -2. Now we have to graph these last because we kind of have to know, where the graph is before we can erase and put in the little hole. So I find those first by looking for cancellations, but you have to add them to the graph very last. So what I usually do is put a star on the graph to remind me to put the hole in. And you can think of maybe a method that will help you remember. The next thing to look for is the vertical asymptotes. So you look in your denominator and see what factors are left that might cause division by 0. And so we have a vertical asymptote with an equation of x equals 4. And I'm going to sketch that right here in red. The function will not cross that vertical asymptote. Now we can focus on our numerator. The x-intercept is going to occur at the x value 7. So I'll add that to the graph. And again, that came from the numerator. And the y-intercept we can find by plugging in 0 for x in the function. 0 squared minus 5 times 0 minus 14 over 0 squared minus 2 times 0 minus 8. We're just substituting the x value 0 into the function. So that ends up being a negative 14 divided by a negative 8. And on a graph, a decimal usually helps me find my placement the quickest. So in this case, that's going to be around about 1.75. So on the graph, I'll just kind of get it in approximately that correct spot. Okay, the last thing to think about is that end behavior asymptote, what's happening on the far right and the far left hand side of the graph. We compare the degrees of the function. In this case, the two powers are the same. So our horizontal or end behavior asymptote is going to be equal to the ratio of their leading coefficients. We've got 1x squared and we're dividing by 1x squared. That's going to be equal to 1. So up here at the y value 1. Okay, now we can sketch in our branches. Remembering before what that shape looked like, that upper branch is going to nestle between this asymptote and this one, and I make sure that I hit that y-intercept. So that's the first branch, and I remember that I have my hole, so I'm just going to erase a teeny bit of the graph right there and draw that hole in for the x value negative 2. And then the other branch is going to be down here nestled here. Make sure you hit that x-intercept like so. So when we graphed polynomials before, we had domains of all real numbers. They didn't have any division in them, so there was no problems with dividing by 0. But with rationals, we have to be careful about the excluded values. So when we're writing the domain of these functions, it's almost all real numbers. The graph is very smooth. It covers almost the entire x, almost all of the x values, but we have two issues on this graph. X cannot be equal to negative 2. That's the location of the hole, and x cannot be equal to 4, which is the location of the vertical asymptote. And I want to show you the table of values. And you can see on the table of values that we have, let me bring that in front of the, maybe, there we go, order. There we go. You can see on the table of values that at negative 2, that's the top line, and at 4, we have errors. None of the other x values cause any problems in this function, but for those two values, negative 2 and 4, it is undefined. So you can sometimes use the table if you want to kind of check and see what is happening. Okay, so that's our first graph. Let's do another one. This function is the function x divided by the quantity x squared minus 25. So again, I usually like to graph it first and just see what it looks like. This one on the calculator screen looks something like this. Sometimes the calculator screens can be tricky to interpret on rational functions because the calculator has some limitations with asymptotes. But what this one is really looking like is it has a branch here, and it has a branch in the center that looks something like this, and that is connected, and then it has a branch over here on this upper right hand corner. So that's the shape of our function. So let's go ahead, and I'm just going to kind of sketch that shape right here so that when I go to graph it, I'll know what it looks like. Okay, so now I factor it. Well, my numerator is just an x. That's already factored as much as it can be. The denominator here factors as x plus 5 times x minus 5. And I'll go down my list looking for different features. The first thing I look for is holes. They come from cancellations. In this case, nothing cancels, so there is no hole. The vertical asymptote comes from things that cause division by 0 from the denominator. We've got two vertical asymptotes at -5 and at +5. So I'll sketch those on the graph. Continuing down that list, I look for my x-intercepts. They come from the numerator. The factor x is in our numerator, and sometimes the factor x gives people problems, but the value that makes the numerator equal to 0 is that x has to be equal to 0. So we've got the numerator. Sorry, we've got the x-intercept at 0. Now you may realize that that's also going to be the y-intercept because you can see it right there on the y-axis. But in case you didn't notice that, if we substitute 0 for x, we get 0 divided by 0 squared minus 25, which is 0 divided by -25, which is 0. So we have already marked that y-intercept as well. For our end behavior asymptote, the horizontal asymptote, we need to compare the degrees. In this case, we have a larger degree in the denominator, so that means that our end behavior asymptote is going to be at 0. Anytime you have a larger degree in the denominator, it's going to have an end behavior asymptote at 0. So we've got our asymptote sketched there. Now we can use our shape that we got from our calculator to sketch it in. We've got the branch here that nestles in between these two asymptotes. And we've got one over here as well. And then the center one, the center branch kind of comes down over and through that intercept and then continues down here. So the domain of this function would be all real numbers with the exception of -5 and 5. You can write that as a plus or minus if you want. All other x values are well defined for this function. We just have those two discontinuities. All right, so that's our second graph. Let's go to a third graph. This is x squared divided by x squared minus 9, in some ways similar to the last graph, and in some ways quite different. So if we graph it, it looks like this. So it still has 3 branches, but the branches are different. Sometimes I call this one the creeper face. Kind of looks like that. So if we factor it, we end up with x squared divided by x plus 3 times x minus 3. Once again, we don't have any cancellations, so we don't have any holes or anything on our graph. But we definitely have two vertical asymptotes. They come from those factors in the denominator. We have vertical asymptotes at positive and -3. Okay, x-intercepts come from our numerator. Our numerator is x squared. When will x squared equal 0? Well, it will only equal 0 if x itself is equal to 0. So we've got our x-intercept at 0. Y-intercept, if I substitute 0 in for x, you may have already noticed that it's 0, but we end up with 0 divided by -9, which is 0. So that's our y-intercept as well. For the end behavior asymptote, we compare the degrees. In the numerator is degree 2, in the denominator is degree 2, so we compare those leading coefficients. We get 1x squared divided by 1x squared, which is equal to 1. Okay, so we can sketch in our function now. We have this branch here and another branch here nestled between those asymptotes. And then we have kind of an upside down parabola shape, though not exactly a parabola, that comes up and hits that origin intercept point right there and then back down. Now you might have noticed that there's kind of a gap right here where there's no branches sort of a part of that. That lower branch does not come up and touch that horizontal asymptote. There is a gap there. That gap would show up in the range if you were writing the range. The range would be from -infinity to 0 and then from 1 to infinity. But that's fine. There's no issues there. It's fine. Sometimes looks confusing, but for the domain, we didn't have any holes, so our domain is going to be all real numbers except for those two x cannot equal, +3 or -3 are two vertical asymptotes. Okay, almost done. 2 more graphs. I know it's a lot, but there's all these different scenarios that come up. Here's a function, x squared plus 9x plus 18 is being divided by x cubed plus 6x squared. If we graph that in the calculator, it looks like so. Some people say it looks like maybe a volcano. So I'm going to sketch that kind of shape. And then we can use our mad math skills to place that on the graph properly. So for the factored form of this function, the numerator factors as an x plus 6 and an x plus 3. The denominator has a common factor of x squared that we can factor out, and that would leave an x plus 6. So first thing we look for is cancellations or holes. We have a hole at the x value, -6. I'm going to put a star on the graph to remind me to put that hole in the function when I sketch it. So vertical asymptotes come from any factors left in the denominator. We just have a factor of x in the denominator. That means this thing is going to have a vertical asymptote at 0. Sketch that in. X-intercepts come from the numerator, so we're going to have an x-intercept at the value -3. I'll plot that on the coordinate plane. And the y-intercept we find by substituting 0 into the function for x. So in this case, we would get 0 squared plus 9 times 0 plus 18. That's divided by 0 to the 3rd plus 6 times 0 squared. That's 18 divided by 0, and that is undefined. It means we don't have a y-intercept, and if you think about the location of that asymptote, that kind of makes sense. If we have an asymptote right on the y-axis like that, it means that the function is not going to cross the y-axis, which is the definition of the y-intercept. So there is no y-intercept. All right, last thing, end behavior, compare the degrees. We have a higher degree in the denominator, which just means that our end behavior asymptote is going to be at 0. So there's that last asymptote. Okay, now we can sketch the function. On the right-hand side, it kind of gets close to that asymptote, something like this. On the left-hand side, it does actually dip below at that intercept, and it kind of approaches that asymptote from below instead of from above. The last thing, that star there, is to remind me to draw the hole on the function, and it's right there at that x value -6. So the domain is going to be all real numbers with the exception or the exclusion x cannot equal -6. That is not defined for this function. It's a discontinuity or a hole. And also x cannot equal 0. That's the vertical asymptote kind of in the middle. Okay, last one. 5 minus 5x squared is in our numerator, and we're dividing by x squared plus 9. If you graph this on your calculator or Desmos, you'll see it looks something like this. I'm going to sketch that just to remember what the shape is, and I'll use my graph features to help me place it on the graph. So the factored form of this is a little bit challenging. The numerator is not in standard form. So I'm going to think of that as a -5x squared plus 5 if it's in standard form. So that does have a common factor of 5. And since my leading term is negative, I'm going to factor out a -5, which leaves an x squared minus 1, which is factorable. So it's going to be a -5, an x plus 1, and an x minus 1. Now that was just the numerator. For the denominator, in the past, we have factored x squared plus 9 using imaginary numbers, and we factored it as an x plus 3i and an x minus 3i. But as we work with rational functions in this unit, we're going to limit ourselves to real numbers. So we're going to just leave that as an x squared plus 9, and we're going to say that it is not factorable. So we look for cancellations first. There are no factors that cancel. That means there are no holes. The vertical asymptote comes from the denominator equaling 0. It comes from numbers that cause us to divide by 0. In this case, our denominator is x squared plus 9. For any x value, if we square it, we get a positive number, and we're adding 9. So there are no numbers or no x values that make x squared plus 9 equal to 0. So that means no vertical asymptote. And if you're ever confused or just like unsure of how to find that vertical asymptote, sometimes just looking at your graph can help, and you can see from the graph I have displayed that there's just not a vertical asymptote in this particular function. So no vertical asymptotes. Now the x-intercept comes from the numerator, so it looks like we're going to have two of those. I have two factors up there. Their x-intercepts are going to be at -1 and +1. So I'll draw those on the graph. The y-intercept comes from, we can find it by substituting 0 for x. So that's going to be 5 minus 5 times 0 squared divided by 0 squared plus 9, which the numerator is 5, the denominator is 9. That's about 0.6. So just a little bit below 1. The last thing to look for is that end behavior asymptote comes from comparing the degrees. The degrees here are the same in the numerator and denominator, so I'm going to think about those leading coefficients. So -5 is the leading coefficient of the numerator, 1 is the leading coefficient of the denominator. So our end behavior is going to approach -5 on the far right and the far left. Okay, so we can sketch our function now. It's this kind of bell shape or anthill shape. It's very close to that horizontal end behavior asymptote, kind of curves up, hits those intercepts, and then curves back down. So the domain of this function, it doesn't have any discontinuities, it doesn't have any holes, it doesn't have any vertical asymptotes, so the domain is all real numbers. So as you're graphing these, really use that list of features to help you place all of the different features of the graph on the coordinate plane. They are definitely challenging at first, but you will get the hang of them. Thank you.